Alrighty guys, let's go ahead and get started with this problem here. It says consider a giant steel beam of mass 68 kilograms and length 100 meters that you want to balance on a pivot point at 25 meter mark. There is a 70 kilogram mass located at the 14.4 meter mark as well. So first thing I recommend we do is go ahead and draw a picture of what's happening over here. So I'm going to draw my beam really quickly. So here is my beam, and then I'm going to label what's happening. It says my beam is 100 meters long. So from here to here is 100 meters. It says my beam has a mass of 68 kilograms. And it says that I have a pivot point at 24 meters. So probably somewhere around here is the 24 meter mark. And I'll go ahead and mark that up here. And then it says there is a 70 kilogram mass located at the 14 meter mark, so 14.4, and this is 70 kilograms. Okay. It says what is the magnitude of torque supplied by the 70 kilogram mass? So let's start off with that. We know that torque is equal to force times the distance from the pivot point. The force in this case is force gravity because this mass is pulling down on the beam. So I would have torque is equal to force gravity, which is mass times gravity times r. So something that people keep forgetting is that r does not mean the radius. R means the distance between the pivot point. So if we have our distance right here of 14.4 meters and the pivot point is 24 meters away, that means that the distance between those two is 24 minus 14.4. When we do this, we're going to go ahead and solve, and we find out that our torque should be 6,585.6 Newton meters. Next, we want to figure out the torque supplied by the steel beam. Well, we said the steel beam has a mass of 68 kilograms and a length of 100 meters. Since it's a uniform steel beam, that means that all this mass can really just be located right in the middle, which is 50 meters. So if we're looking for the torque of the steel beam, we know that the force is going to be the mass, which is 68, times 9.8, times r. Again, r is the distance from the pivot point. So r would be this distance right here, because our center of where this mass is located is 50 meters minus 24 meters. When we solve for this, we find out that our torque should be 17,326.4 Newton meters. Now that we've figured out both of our torques, we want to find out what the net torque is. We know that net torque is just equal to one of our torques plus the other torque. The thing that's important here though is that we have two torques and each are on different sides of the pivot point. So our torque on the left side, this 70 kilogram mass, is going to pull our bar in this direction, supplying a counterclockwise torque. And then the beam itself would pull down this way, supplying a clockwise torque. So we know that clockwise is negative and counterclockwise is positive. So when we add these up, it's going to look something like this, where positive torque is going to be my 6,585.6 Newton meters minus the torque acting in the opposite direction, which is 17,326.4 Newton meters. Go ahead and add those two together, and we find out that the net torque should be negative 10,740.8 Newton meters. Alright, now that we're done with the easy stuff, let's do something a little bit more challenging. Where would we have to place a 330 kilogram mass to make the steel beam balance on the pivot point? So if we look at these two values here, we have 6,585 Newton meters of torque on the left hand side and 17,326 Newton meters of torque on the right hand side. So if we want this to balance out, we can already see that we're going to need to place this 330 kilogram mass somewhere on this side of the pivot point. So a way that I would approach this to figure out exactly where I need to place it is I would take what my net torque is and set it equal to the torque supplied by the 330 kilogram mass. The reason I'm doing that is because I know that if my 330 kilogram mass has a torque equal to this net torque, then there will be 0 net torque on this beam, meaning that it will balance out. So torque is equal to F times R. My torque should be equal to 10,740.8. My force is 330 times gravity, 9.8, times R. When I simplify all this and solve, I find out that my R value should be equal to 3.32 meters. So before you go ahead and make a mistake here, we need to think, what is this R value telling us? Is that telling us where we are placing our mass on the beam? So we're going to place it at the 3.32 meter mark? No. What that R value is telling us is that we are placing our mass 3.32 meters away from the pivot point. So therefore, we want to place our mass 24 minus 3.32 meters on this beam. And we find out that our mass should be placed at a distance of 20.68 meters. Now it asks us what our net torque will be with the mass placed at 20.68 meters. Well, again, if it's balancing, that just means that the net torque in this case has to be in equilibrium, which means that it's just 0 Newton meters.